This is part 3 of our introduction to physics. And today, last time we looked at, we continued on with measurement in units, and we looked at scales and orders of magnitude and the types of quantities and the types of fundamental units. So now we're going to build onto that and move on to something more complex, and we're going to look at, finally, real physics, and we're going to look at motion. And really, in this course, we deal with three main types of motion graphs that we use to measure quantities. The first is graphs which compare distance and time. The second are graphs which compare velocity and time. And the third is acceleration time. So this might be a bit of a long video because we're going to go through their basics, and then we're also going to do sample questions. So it might be split into two parts, but we'll see. So let's look at the first, distance time graphs. Compares distance traveled in a given time, which is speed. And that's because, well, if you look at speed, it's simply the change in distance over a change in time. And so the slope of the line actually tells us the speed of an object. Right? And let me explain why. So we have the equation for the slope of a line is simply the change in y, right, over the change in x, right? That's m. So y is this variable over here, and x is this variable here. Now, if we just plug in the variables, what we find is that it just becomes d delta d, which is delta means change, and delta t, which is simply the equation for speed, right? Distance over time. And so that's why if you find the slope of a line, let's say it's the blue line, which is 10 over 2, right? Change in y is 10, and then change in x is 2. You can just find the speed. And so for this blue line, for example, we do that here, 10 meters in 2 seconds. We can calculate that, right? We can just do that the exact same way, and we get 5 meters per second. And the slope of the line is also 5, right? 5 and then 1. So the slope, you got to remember, in a distance time graph, the slope will always tell you the speed or the velocity. 0 is obviously taken as our starting point, right? So that's our point of reference. That's where we begin our journey. If our slope is positive, then that means we're moving away from our starting point, so our velocity is positive. If the slope is negative, our velocity is negative. If the line is straight, then our velocity, if the line is straight, then our velocity is constant. If the line curves, then that means we're accelerating, right? So as you can see, this blue line here, we have steady speed, right? Because our slope is constantly the same, so our speed is always steady. If the line was, let's say, curved like this, then that would mean we're accelerating because the slope keeps increasing, hence the speed keeps increasing. So you can always calculate the average speed, which is just the total distance divided by the total time, right? And let's do that, okay? So let's say we want to find the average speed at this point here, okay? And if we want to do that, so we have this point here. Let's say the line was a curve, right? It was like this. It still wouldn't matter because we're looking at the total distance only and the total time. So the average, and that's what matters. So it's not really important. So what we can do is total distance is 8 minus 0, right? 8 minus 0, which is just 8 divided by 4. 4 minus 0, which is just 4, right? And so we get 2 meters per second was our average speed. And so regardless of the shape of the curve, as long as you do that, you'll get your average velocity, mind you, because because we are looking at negative versus positive. So I use velocity and speed interchangeably here, but what I really mean is velocity. So we can always calculate the average velocity, and the area under the curve is nothing really useful because we'll find out later with the other two graphs. They actually do tell us useful information, but here it's not very useful. And a flat line means that the object is stationary, i.e. it's not moving. Okay? So that brings us to, here's another image which kind of shows you how distance and time work with each other, right? So curve upwards shows acceleration, slope gradient shows constant speed, steeper gradient means faster, and you can just read these if you want to summarize exactly. Okay, so a velocity time graph compares change in velocity over the change in time, which, if you were catching on to what I said last time, is actually just the acceleration. So, as you can see here, the slope of the line, just like the last one, will tell you the change in velocity over the change in time, which is the acceleration. So, steeper slope, right, means greater acceleration, and a negative gradient indicates deceleration or negative acceleration. And a flat line means a constant speed, right? We're constantly moving at 3 meters per second right here at this blue line. And a positive velocity means we're increasing displacement. And a negative velocity, so if, let's say, this graph went into the negatives as well, then if it was over here, then that means we're moving in the opposite direction, right? In the negative direction. And here's another thing. The area under the curve will tell us the distance traveled. So, for example, if we want to find out the distance traveled, well, we'll calculate the area, and it'll be basically base times height, right? And what is our base? Our base is time, and our height is just distance over time, right? So if we multiply the two together, we just cancel out the time, and what we end up with is distance. So that's a mathematical explanation as to why the area under the curve will give us the distance. It's pretty simple. You just cancel out the time. And so let's say we want to find out the distance traveled over here. We just find the area under the curve, right? So we do 3 over here multiplied by 4, and because it's a triangle, we divide it by 2, and we get 6 meters. So pretty simple. Alright, and then we go to an acceleration time graph. This is, also, I should also point out, this is kind of the reason why I think that velocity time graphs are kind of the most useful graphs. And the reason for that is because it's very easy to derive the distance and the acceleration, right? Because you just calculate the slope and calculate the area. You don't need to use any complicated math, it's just one step. So whenever you have a velocity time graph, remember that. Remember that you can always calculate the other two if the line is straight, right? And that brings us to acceleration time graph. This is the rarest of the three, and there's a good reason for that. It's just because it's kind of limited as to how much you can do with it. But basically, a flat line means constant acceleration, right? So if it's stuck at 2, that means we're constantly increasing our speed by 2. If the line is at 0, then velocity is constant, like over here. But as you can see, because the curve is at 2 here, our velocity is increasing constantly by a slope of 2. And the slope is the rate of change of acceleration, which is nothing that useful. But the area will tell us the change in velocity. So if our initial velocity was 0, then the change in velocity will be the actual velocity, but then obviously that might vary. So it'll be the change in velocity, right? So you can calculate the area under the curve. Let's see, 2 times 10 over here is 20. And if we go to T10, something doesn't quite add up here, but actually, no, it doesn't quite add up in this graph, but it would basically be, the change in velocity would be 20 meters per second. And so the area under the graph will tell us the change in velocity. This isn't really to scale, this is just to show you the shape of the curve, right? So as you can see, area is a flat, acceleration is a flat line, so the velocity is steadily increasing, and the distance is increasing in a curve, right? And so this is just to get the shape across, so you can understand it visually. And so that covers all three. This is a good way to remember the relationship. So acceleration is just the if you find the area under an acceleration time graph, then you'll get the velocity, and then if you do that, the area of that, you'll get distance, and then so you have this sort of cyclical pattern, right, where you calculate the slope, you find the next one. And I find this kind of useful to help me remember, because that way, if I'm ever on any graph, if I want to find the velocity from an acceleration graph, I can just find the area, and vice versa. So you have this kind of useful circle to help you remember. So do take note of that if you like. And I think that'll wrap it up for now. Watch the next part of this, because we're gonna go over some example questions. So definitely watch that. And thank you for watching.